First, we will learn about few fundamental terminologies that we frequently come across when we study or discuss about AC circuits. The first thing is resistance. I have already discussed in one of my previous lectures about resistance, inductance and capacitance in more detail. So resistance is the DC component or the passive element that we have in our AC circuit, where we know that the resistance is the property of a conductor by virtue of which it opposes the flow of electrons or flow of current. It is represented by R and the unit of resistance is ohm. The opposite or reciprocal of resistance is called conductance, and it is the property of a conductor by virtue of which it helps the flow of electrons or currents, and the unit is mho or Siemens. Now the next component or AC component that we have in our AC circuit is inductor, and inductance is the property of a conductor by virtue of which it opposes any change in magnitude or direction of electric current that passes through the conductor, and the unit of inductor or inductance is Henry. Now we have another AC component in AC circuit, which is capacitor, and capacitance is that property of material by virtue of which we measures the capacity of that material to store electrical energy or electrical charges in it. The next terminology that we frequently come across in case of AC circuit is reactance. In AC circuit where we have AC components like inductor or capacitor, there we come across this terminology reactance, and it is the measurement of the opposition imposed by the inductor or capacitor towards the alternating current. So you can say that it is a kind of resistance in case of AC circuit by AC component. So what resistance does in case of DC circuit, the same thing is done by reactance in case of AC circuit by the AC component like inductor or capacitor. So if it is done by inductor, then it is called inductive reactance, and the unit, as you can see here, is the same as resistance, that means ohm. And inductive reactance is measured by omega multiplied by L, where L is the inductance of that inductor and omega is the angular frequency of the supply, and the unit of that angular frequency is radian per second. Since in case of angular frequency, it is measured in terms of angular distance, and angular distance is measured in terms of angle, and the unit of angle is, we know that it is either degree or radians. So here the angular frequency is radian per second, and the relationship between angular frequency and the other frequency that we know, which is linear frequency, that is omega is equal to 2 pi f, where we already familiar with linear frequency, and that is the frequency that is measured in terms of the distance we cover linearly, and the unit of linear frequency is cycles per second, and that is also we term as hertz. So the inductive reactance, if we want to express in terms of linear frequency, that is 2 pi multiplied by linear frequency, which is f, multiplied by the inductance of the inductor. Now there is another kind of reactance which is imposed by the capacitor, and that is called capacitive reactance. And the capacitive reactance, which is symbolically represented by X, capital X suffix C, that is measured as 1 by omega C, where omega has the same meaning, angular frequency, and that is related to the linear frequency by same expression. So 1 by omega C, or we can say 1 divided by 2 pi fc, and the unit is again same as resistance or inductive reactance, which is ohm. Now there is another term which is called susceptance. Now susceptance is the property which is same as or equivalent to conductance. Conductance, what it does, conductance is the property which we know is helps in case of conduction of electrical current or electrons flow. So here the susceptance as also has the same property, or it is the measurement of that how much that inductor or capacitor helps that alternating current to flow through it. So in case of AC circuit, there is again two types of susceptance. If it is imposed by inductor, that is called inductive susceptance, and that is symbolically represented by capital B suffix L. And since it is the reciprocal of reactance, so it will be 1 divided by X of L or X suffix L, and that is 1 by omega L. And unit wise, it also has the same unit as a conductance, and that is Siemens. In case of capacitive circuit, or in case of capacitor, the susceptance is called capacitive susceptance, and that is 1 by xc. So it will be finally omega multiplied by c, unit is same, and that is Siemens. Now in case of AC circuit, where along with inductor and capacitor we have also resistor, that means it is not pure inductor. With inductor there is a resistor, so it is an impure inductor, or you can say it is a series RL circuit where we have resistor and also inductor. And in case of capacitor, if with capacitor there is a resistor, that means it is not it doesn't work as a pure capacitor, then in that case it will be referred as a series RC circuit. So if it is a series RL circuit or series RC circuit, or it is not a pure inductive or pure capacitive circuit, there a new term is introduced, and that is called impedance. Impedance is the measurement, we can say that how much the alternating current is impeded, or we can say again it is the measurement of opposition. So how much it is impeded or opposed that alternating current by that RL circuit or that RC circuit. So generally or mostly when along with inductor we have resistor, we find out the impedance value of that RL branch or RC branch. And impedance also does the same thing as resistance does, so it is again an opposition. So Z, and the impedance is symbolically represented by capital Z. And again there are two types of impedances. So if it is in case of RL circuit, then that is represented or measured by R plus J XL. And this, so in case of impedance, it will always have, if it is suppose for RL branch, then it will always have a real part and imaginary part. So it will always have this format A plus IB or A plus JB. So this reactance will be always a complex value or complex representation, and the unit of impedance will be ohm. And in case of capacitive circuit, means if it is a RC branch, then for that the impedance is represented by capital Z suffix C, and it is R minus JXC. And here also the unit is same, and that is ohm. Now in case of AC circuit, we have another important term which is admittance, and admittance is the reciprocal of impedance. That means if impedance opposes the alternating current to flow through that branch, then admittance is the property which helps the alternating current to flow through that branch. So you can say the admittance has the similar kind of nature of conductance. What conductance does or susceptance does, the admittance also has the same property. Basically it is the property, or it is the measurement, we can say, that how much the alternating current is admitted or allowed to pass through that branch, RL branch or RC branch. So symbolically it is represented as YL if it is for RL branch, and that is the reciprocal of impedance, so 1 by ZL. And unit wise it has the same unit as conductance or susceptance, so it is Siemens. And in case of RC circuit, it is Y suffix C, and that is 1 by ZC. Capacitive, it is called capacitive admittance, and unit is also Siemens. So these are the terminologies that we frequently use in case of AC circuits, then there is another important terminology which is called phase difference. Now, by phase difference, we can, in simple words, we can understand this way, that as in case of human life, also we have different phases. Sometimes it is up, sometimes it is down, sometimes positive things happen in life, sometimes negative things happen in life. In case of alternating current, also, like if it is sinusoidal, then we know that sinusoidal has the nature when it is a periodic waveform, and the periodicity is 2 pi. So for pi, for the half cycle, it has the positive value, and for the next half cycle it has negative value. Now there will be a moment when the value of that sine wave or sinusoidal signal will have a minimum value. There will be a moment when that waveform or signal will have maximum value. There will be a duration when it will increase. There will be a duration when it will decrease. There will be a duration when the value of that signal will be always positive. There will be a duration, means the next half cycle, when the value of that signal will be negative. And since in case of AC circuit, the voltage that we apply, and for that, if we take voltage as the cause, and because of that, if the voltage is supplies some current, and that we take as effect, then if we suppose supply AC voltage to that AC circuit, then the current that we will be getting in that circuit, or which will flow, that will be also AC in nature. So when in an AC circuit we are applying AC voltage, and because of that we are getting AC current, that voltage and that current will have alternating nature. So if it is suppose sinusoidal, then for both the cases, for voltage and current, there will be a moment when that voltage value will be minimum or the voltage value will be maximum. And for that is applicable for current also. There will be a moment when the current value will be minimum, and there will be a moment when the current value will be maximum, and so on. So it's not always mandatory that when the moment when the voltage value is minimum, at the same moment the current value is also minimum. If it is that at that particular moment the voltage and current, they are having the minimum value, or the moment when both of them are having the maximum value, then we say that the voltage and current are at the same phase. Like when voltage is minimum, current is also minimum. When voltage is maximum, the current is also maximum. When voltage is increasing, the duration for which voltage is increasing, current is also increasing. When voltage is at the positive half cycle, current is also at the positive half cycle. So what is happening for voltage, the same thing is happening for current also. That means we can say, in simple words, we can think this way: the current and voltage, they are at the same phase. But if it doesn't happen that way, like if the voltage is suppose at minimum, the current is not at the minimum value, that doesn't have the minimum value, but it has some other value, like it may be some 50% of the peak value. Or we can say when the voltage is at peak, the current doesn't have is not at peak, or it doesn't have the maximum value, or it has some other value. So in that case, or in that sense, we can say the voltage and current are not at the same phase. There is a lag between the phases of that voltage and current, and that difference is called the phase difference. So when the voltage and current in case of AC circuit, one is effect and one is cause, they are not at the same phase, then there will be a difference of phases between them, and that difference is called phase difference. Now we will understand more about this phase difference in next few slides. Here, this waveform, as you can see here, we have a circuit where we have only a resistor. So it is a purely resistive circuit, and we are energizing this resistive circuit by an AC voltage source, and this AC voltage is supplying an AC current. Now suppose since this is a sinusoidal, suppose this is a sinusoidal voltage, so we know the format of sinusoidal voltage. So V, where small v represents the instantaneous value of that voltage, means at any instant, if we want to know the value of that voltage, we can measure from this expression. and Vm, it stands for the maximum value of the voltage. So since it is alternating in nature, so definitely there will be a moment when it will have maximum value, and that this Vm measures that maximum value. Vm then sine omega t. So whereas the t will vary, or as the omega t, which measures the angle, omega t will vary, this small v will vary from moment to moment. Now, if it is a purely resistive circuit, in we can derive easily, and that will be explained in my future classes, that that voltage and current in case of purely resistive circuit, they are at the same phase. That means there is no phase difference, and or the phase difference is zero. So if the voltage has this expression Vm sine omega t or this format, then current that passes through that resistive circuit, that will also have the same format, and that is Im sine omega t. Definitely the maximum value of that current may be or may not be same numerically. So we are representing here by some other symbol, which is Im, and it is sine omega t. So if we put omega t is equal to here 0, the value of this voltage will be 0. If we put omega t is equal to 0, the value of the current signal will be also 0. If we put omega t is equal to pi by 2, that means sine omega t will be 1. So we will have Vm, that is maximum value of peak, it will be at peak. Now similarly, if we put here omega t is equal to pi by 2, again sine pi by 2 will be 1. So I will have the maximum value, or current it will be also at peak. That means what is happening, the phase wise, what is happening to voltage, the same thing is happening to current also. And graphically, if we see here, here we can see this voltage, the waveform which is drawn here in blue, that represents the voltage, and which is drawn in red, that represents current. Here the current, the circuit has been chosen such a way that the current value is less than the voltage. That depends on the circuit configuration, and that depends on the value of this resistance. If the resistance, suppose the value is 1, then the value of this voltage and current will be same. So the resistance, the value was chosen such a way that the current value is always is less than the voltage, so that we can differentiate graphically between voltage and current. Now here, this is the point where the voltage has the minimum value, or you can say voltage was just started, omega t was 0. Here this yellow lines basically represents, this is the x-axis and this is y-axis, and this is the cross section of the origin. So where the omega t value is 0, and when omega t value is 0, the value of that voltage is also 0, and the value of the current signal is also 0 here. Now when omega t has value pi by 2, here we know the relationship between radian and degree, where it is pi radian then 180 degree. Here the leveling has been done for the axes in radians. So we know that the approximate value of pi is 3.14. So 3.14 radian is equal to 180 degree. So here this point is near about 3.14. So this measures 180 degree or pi radian. So we know in case of periodic AC waveform of signal, the periodicity is 2 pi. That means for a half cycle, the angular measurement is pi. So between this point and this point, it is pi, and between this point and this point, that is another pi. So altogether, for the whole periodic waveform, or for the complete cycle, the angular measurement is pi plus pi, it is 2 pi. Now 3.14 in our case, it measures pi. So pi by 2 will be 3.14 by 2, and at pi by 2, it will have the maximum value, the voltage, or it will be at peak. And we can say roughly, if it is, say this is pi by 2, then the voltage is at peak, and also we can see here that the current is also at peak. And when now after that, when the voltage starts decreasing, the current also starts decreasing, and at this point, means at pi, the voltage again has the minimum value, which is 0. The current also has the minimum value, and after that it enters into the negative cycle. So between this pi and 2 pi, the voltage will have the amplitude of all the voltage signals at any instant will have always negative value. And see, that same thing happens in case of current also. Between pi and 2 pi, at any instant, if we consider, the amplitude of that current signal will be negative. So this is the concept where the phase is same between voltage and current. Now we will see another example where the phase of voltage and current will not be same, will be different. Now for that we have chosen a circuit where we have an inductor, and that inductor is energized by an AC voltage signal which is supplying an AC current. Again, voltage is represented by small v and current is small I. This is a purely inductive circuit where we don't have any resistance, only we have a pure inductor. Now if current we take as a reference, signal will be represented as I will be equal to Im sine omega t. Now if we put omega t is equal to 0, then the value of that current signal will be 0. So this is the point or the origin where this x-axis and y-axis they intersect here. The x-axis represents the omega t, the angular means theta we can say, and y-axis represents the amplitude of that voltage and current signal. Now current has been taken as a reference, and again in my future class I will explain that how the phase difference between voltage and current is 90 degree for a purely inductive circuit. So the phase difference, as I said, between voltage and current in case of purely inductive circuit is 90 degree, and that's why the expression of the voltage signal is like Vm sine omega t plus 90 degree. And graphically it has been shown like current signal is starting here at this point, then this point where it is around 3.14 or pi, it completes one cycle, the positive half cycle, and then between pi and 2 pi it has another cycle or negative cycle. So between this 0 and 2 pi it has the complete cycle. Now in case of voltage signal, what we can see here, unlike the previous circuit or the purely resistive circuit where the voltage and current were starting at the same point, they were at the same moment, they were at the peak, here it is not like that. Here the voltage is starting before current here at this point. Now as we have seen here that the phase difference between voltage and current is 90 degree. So this gap is actually 90 degree, this difference, and that is the phase difference between current and voltage. So this is the measurement of positive phase difference. So we can also think this way, that the current is starting at this point, but before current the voltage has started, and this gap or difference is 90 degree, and this way we can take this phase difference as positive phase difference. And suppose if instead of starting here the voltage, if it was starting at this point, maintaining the gap of 90 degree, then we would have said that the voltage is lagging. So when the current is starting, then after 90 degree phase angle or phase, the voltage is starting. So in that case we would have said that between voltage and current the phase difference is 90 degree, but voltage is lagging the current. But in this case voltage is leading the current. Yeah. Now in the next example we will see another circuit where along with inductor we have here a resistor. So this time it is not a purely inductive circuit, this is a RL circuit or RL series circuit, and again here we are applying an AC voltage source of AC voltage which is supplying AC current. Now again current we are taking as reference, so I is equal to Im sine omega t, and since this is, though it is not purely inductive circuit, but still it will have some inductive property, and because of that the voltage again will lead the current. But here the phase difference will be no more 90 degree, rather it will be less than 90 degree. Now if we express voltage, it will be V will be equal to Vm sine, this time omega, it will not be omega t plus 90 degree, rather omega t plus some angle phi which is less than 90 degree. And graphically also if we represent, then this represents the same origin. This is the omega t axis or the x-axis along which the omega t varies or t varies, and this is the y-axis along which the v and I vary. But here I, this is the current, the waveform of the current, and that has been taken as reference. So with respect to that, now the voltage will be plotted, and here the voltage is leading. So voltage will be as per leading phase angle. Voltage will start before current. So this gap, as we know, will be taken, this difference will be taken as positive, or this will measure the positive phase difference. But this time this difference is not 90 degree, rather it is less than 90 degree. So value wise, if we see, then it will be less than that value that we have seen in the previous case. So it was previously, when it was purely inactive circuit, it was 90 degrees, so it will be less than that. Now next we will see purely capacitive circuit. So here we have only capacitor and we don't have any resistor, and same way we are energizing by an AC voltage and it is supplying AC current. So this time we are taking the voltage as reference. So V will be represented as Vm sin omega t. We can take I also as reference, the way we took for inductive circuit. So V is equal to Vm sin omega t, and with respect to that, now current will be represented or plotted. So V first will plot, and this is again the origin. So here the voltage signal will start or will have the minimum value, that is 0. So with respect to this point, now if we think or if we visualize the waveform, so it will be like the voltage will be between these 2 points, it will have positive half cycle, this is 3.14, and between this point and this point, which is 2 pi, will have the negative half cycle, and this between 0 and 2 pi it will have the complete cycle, and this is the one waveform. Now if with respect to voltage, now if we represent the current, then it will be Im sin omega t plus 90. Here the current is leading voltage. Previously, when it was purely inductive circuit, the voltage was leading current by 90 degree, and if when it was impure, the voltage was again leading current, but that angle was less than 90 degree. But in case of purely capacitive circuit, the voltage is lagging, current is leading. As you can see here, if we take voltage here as reference, then when we go towards left, that measures the positive phase angle. So here again I will derive in my future class that how the phase difference is 90 degree between voltage and current, and how current leads voltage in case of capacitive circuit. So here this again measures 90 degree, and in case of purely capacitive, that phase difference is 90 degree, and I, or the current, leads voltage in case of capacitive circuit. Rest is same as far as the understanding is concerned. Now next we will have the circuit where along with capacitor we will have also a resistor. So this is no more a purely capacitive circuit, and the voltage and current have the same meaning. Again we are taking voltage as reference, so V is Vm sin omega t, and with respect to voltage, now current we are representing. So I will have that expression like Im sin omega t, and this time again we'll have some phase difference, and that is phi. But since this is not a purely capacitive circuit, so phase difference will not be 90 degree, rather it will be less than 90 degree, and that is represented by phi. But nature wise, I will lead V, or current will lead voltage. So V, if we take as reference, then graphically when we will represent, current will start before voltage, we can say. So when the voltage has minimum value, current has some other value. But previously we saw that since the difference was 90 degrees, so when voltage was minimum value, then current had maximum value, or where that current was at P. So if the phase difference is 90 degree, be it a purely capacitive circuit or inductive circuit, so when one component will have minimum value, the other component will have the maximum value. Likewise, when the voltage will be at peak, the current will have minimum value. That happens in case of pure circuit, purely capacitive or inductive circuit, not for impure. Now in this RC series circuit, again as I said, the current is leading, but the phase difference is not 90 degree, rather it is less than 90 degree. Now there is a word which we can use to remember in case of RL or RC circuit, or maybe purely inductive or purely capacitive circuit, that which component leads or which component lags. This is just a word to remember that phenomena easily. So here C represents capacitor, and L represents inductor, I represents current, V represents voltage. So in case of capacitor, we can think this way. In case of capacitor, I since has been written first or before V, so I leads and V lags. And in case of inductive circuit or inductor, V since has been written before I, if we think in reverse order. Then in case of inductor, V leads and I lags. So as in this capacitive circuit or RC circuit, we can see here that the voltage lags and current leads. So in case of capacitive circuit, in case of capacitor or capacitive circuit, current leads and voltage lags.